So this is where we left off. We want to show another one. Sine of 1 over x as x approaches 0. So we can see you can't substitute directly in for 0. Sine of 1 over 0 is undefined. So we want to see what happens as you approach 0. So I want to show this graphically, but talk about algebraically a little bit. What happens, though, when x approaches infinity or negative infinity? Then 1 over x approaches 0 in both cases, right? We don't write 1 over infinity equals 0. That is a complete, absolute mathematical fallacy. Don't ever write that. Ever, ever, never, never, ever write that. I'm having trouble even leaving it on this video in case someone happens to walk by and see it. So we got to get this off right away. You never write 1 over infinity equals 0. Okay, ever. Don't do that. So it's a limit equals 0. So that's what happens to the graph. But what happens as you approach 0? That's really the question. So let's just look up the video, which I have ready to go here. So here's, up here is the sine of 1 over x, and I can't point to it in this way, but I'll just show you. So study this for a second. You can see that the function on the outside is approaching, as you approach infinity, you're approaching 0 on both sides. As you zoom in, oops, I want to zoom in both ways. As you zoom in, you can see, no matter how close you zoom, it just keeps oscillating back and forth. I mean, you can't, look at how far, look at that, look at those lines going back and forth, back and forth. So as you keep zooming in, you're never going to get to a value. Okay, so what happens infinitely, you can see that. See the 0.01 on the right, negative 0.1 on the left. What happens then, and that's probably a better view here, is it oscillates between what and what. What does it look like it's doing? So yeah, it looks like it's oscillating between negative 1 and 1. Okay, so it's not approaching a specific value. So it's looking like that graph would do this. And so that's not good enough. That's not really how you do math. You study it that way, and it looks like it does this, and then it dips down, and then it just basically goes, and then it comes back up, and it comes back up, and then that. So that's kind of what it's doing as it oscillates. Okay, so that's graphically what's going on, and then you can show it algebraically, which I will go over this more carefully next time, like this. Okay, so when is sine 0? Sine is 0 every pi n. So this is where you can start. Sine of 1 over x equals 0 if and only if 1 over x is every pi n. And then you can solve it. So we'll go over this later. We'll do those problems. Okay, so this is what I'll do sometimes. I really want to get to this part at this point. And go over the limit laws. So this is all written out this time, and I'll just talk about it. I don't always do this, but sometimes we got to just kind of get through. I don't want too many videos, but you do need to write all this up. Writing stuff out is really one of the keys to doing this, even though it's just right there. Okay, so let's see. Let's let B and C be real numbers, right? Those are reals. And N is a natural number, right? 1, 2, 3, etc. Okay, then these are some of the laws. This is 1 and 2. So the limit of a constant as x approaches c is just the constant. So that's pretty silly, right? That's like the limit of 5 as x approaches 15 is 5. Like, there's nothing to substitute in, so it has to be the same thing. All right, so then the limit of just one variable as x approaches c is equal to c. Okay, and then if you do a power, the same thing. Okay, and these can all be proved once we get to the actual definition. So when we get to the definition of limit in 2.3, we'll go through some of those proofs using the definition. So it's axiom, theorem, proof is really, I'm sorry, axiom. We don't have a lot of axioms in this class, but that's the general idea, right? Axiom, definition, theorem, proof. There are other variations, corollaries and lemmas, but that's kind of much later as you go. So here's some more properties. So L, M, B, C are all real numbers. N is natural. F and G are functions, such that limit of f of x equals L as x approaches C. Limit of g of x equals m as x approaches C. So you're approaching the same value, okay, with two different limits. And then you're basically combining the limits with the limit laws. So if you have a constant times the function, and the limit of that function is L, then it's just the constant times L. Okay, and then if you have the limit as x approaches C of f of x plus or minus g of x, then it's just going to be L plus m. Same thing with the product of those two functions, L times m. And then the quotient, same thing. If you do a quotient of those two functions, it's L divided by m, of course, provided m is non-zero. And then a power property as well. So f of x is L. As you approach, raised to a power, and it's got to be natural, right? It's still a natural number because you don't want to like divide by it and get it to be something else. Then you get just L to that power. So with all those limit laws, we're able to, and these are all really, this is a little premature. Normally you do the definition first, but we just want to get you kind of warmed up to the notation before we jump right into the more rigorous definition. So all those are proved by the definition of limit we will see in 2.3. So all those we'll be able to do these limits. And I'll give you a little hint in case you want to get started on it. For this first one is all about factoring. And you need to know difference of squares, sum of difference of cubes. This one is you rationalize the denominator. And this one, you rationalize the numerator before you substitute in your limit value, which we'll go over later. Okay, so one example is pretty straightforward, and then we'll be done with this section. Almost. Okay, so here's theorem. Sorry, not a theorem yet. Let's do an example. So just find the limit. 3x cubed plus 2x minus 1 as x approaches 1. You don't really need those parentheses. It just looks a little better sometimes. So here, there's nothing to really simplify because you're not going to get an indeterminate form, which we'll talk about. So you're not going to get something that's a problem, in other words. We'll talk about indeterminate forms later. So using those laws and combining all those laws, you basically can essentially just substitute in directly to the function. So this would be equal to 3 times 1 cubed plus 2 times 1 minus 1. And then you just evaluate that. And you get 3 plus 2 minus 1, which is going to be 4. So that limit is equal to 4. Okay. So let's look at this theorem. Okay, so this one says let C be a real number and f of x equals g of x for all x not equal to c. In other words, the limit value. So that's true in an open interval containing c. So an open interval and a number line looks something like this. Okay, so an open interval would be like from A to B, and then C is in here somewhere. So it's true within that open interval somewhere. Then the theorem says if the limit of g of x equals L as x approaches C, then the limit of g of x equals the limit of f of x equals L as you approach C. So that basically allows us to do the reducing or canceling of something. So, So basically, it's like saying, 4/6 can be reduced. That is just 2 times 2 over 2 times 3. That's actually equal to 2/3. So it's kind of the same idea. So if you have x plus 2 times x plus 4 over x plus 2, you'd have two different functions that are the same for everything except at C. Okay, because then you reduce this out just like you did to the left there, and you get just x plus 4. So that's what allows us to do the factoring and reducing. So factoring and reducing allows us to do that. I don't like to use the word canceling. It doesn't really, there's no defined way of saying that, so I prefer not to use that word. Okay, so then there's a couple more things I'll leave to you. Theorem of a polynomial, you can just substitute into the polynomial directly. I'll have that in my notes, but not here. Composition of functions, again, you can compose them and substitute in, and we'll look at more examples directly. Indeterminate forms, last thing I want to kind of go over. So indeterminate forms, sorry about my handwriting there, look like this, meaning you can't just leave it like that. We don't know what it is. So 0 over 0 is indeterminate. Infinity over infinity is indeterminate. 0 to 0 is indeterminate. Infinity to 0 is indeterminate. And infinity raised to the infinity is indeterminate. We don't know what it is. We do know m to the 0 is equal to 1 only provided m does not equal 0. So that's something you may have seen. It's anything to the 0 power is 1 except if it's 0. Then you don't know. We call that indeterminate. These go on forever. 2.2 is a long section apparently. We have to look at next, we'll look at the squeeze theorem or the sandwich theorem. Probably go ahead and roll that into starting with 2.3 a little bit. We'll see. We'll have to see how this goes. Okay, moving along.